several pages of problems that are good things to know to prepare for the midterm. Some are theorems whose statements you have to understand and whose proofs you should know. And then there were problems on set theory, on number theory, and on group theory. And I'm happy to go through any ones you want me to start with, and then I'll just choose some others. So any problems you would like me to do? Any preferences? If not, then I'll start with problems in group theory, because that's the most recent topic and the most central one in algebra. So in problem 1, I have a permutation in the symmetric group S10. That means it's a permutation of the integers 1 to 10. 1 goes to 3, 2 to 10, 8, 1, 7, 5, 9, 2, 6, 4. Let me just call this sigma. So that's a permutation in S10, the symmetric group on 10 numbers or 10 letters. And if I want to write this as a product of cycles, so I can start anywhere. I'll start with 1. If I follow through the trajectory, 1 goes to 3. 3 goes to 8. 8 goes to 2. 2 goes to 10. 10 goes to 4. 4 goes back to 1. So this is a cycle that's part of this permutation. So if you just follow through, just iterate this map from the integers 1 through 10 to itself, 1 to 3 to 8 to 2 to 10 to 4 to 1. So this is a 6 cycle. So there's 6 numbers here. And I haven't looked at the number, I haven't used the number 5 yet, so let me see what happens with 5. 5 goes to 7, 7 goes to 9, 9 goes to 6, and 6 goes back to 5. So this is a 4 cycle. And sigma is the product of these 2 cycles. And these are disjoint cycles. So sigma is the product of 2 disjoint cycles. That means the numbers here are different from the numbers here. And disjoint cycles commute. So we could also write, if we want, you don't have to do this, but just to observe, sigma is also the product of 5, 7, 9, 6 with 1, 3, 8, 2, 10, 4. In general, permutations do not commute. You can't write a product in one way and the other way and have the same permutation. But when you have a product of 2 disjoint cycles, then they do commute. So this is the first half of the problem. Any questions about this? And then the second part is to write sigma also as a product of transpositions, that cycles of length 2. So if we want to study this from the point of view of transpositions, there are many ways to write a cycle as a product of transpositions. It's not unique, but one way is just to pair them off in order as you go from left to right. 5, 7, 7, 9, 9, 6. So here we have 3 transpositions. And if you look, this sends 5 to 5 to 7, 7 to 9 to 9, 9 to 6, 6 goes to 9, 9 goes to 7, 7 goes back to 5, so 6 ends up at 5. And if I take this bigger cycle, 1, 3, 8, 2, 10, 4, that's 1, 3, 3, 8, A2, 2, 10, 10, 4. So 1, 3, 3, 8, A2, 2, 10. So this is a product of 1, 2, 3, 4, 5 transpositions. And so sigma, which is this times this, is a product of 5, 7, 7, 9, 9, 6, 1, 3, 3, 8, 8, 2, 2, 10, 10, 4. So here I've written sigma as a product of 1, 2, 3, 4, 5, 6, 7, 8, 8 transpositions. And here, these transpositions are not disjoint. Like these two have a 3 in common, so you cannot interchange them. The order is very important. The symmetric group is not an abelian group. So this is sigma as a product of transpositions, period. There are other ways you can write sigma as a product of transpositions. This is not unique. This is simply one way, and you only have to find one way. Okay. Any questions about this? There definitely is a problem on the midterm that involves taking a permutation and writing it as a product of cycles that are disjoint or as a product of transpositions. This is a fundamental operation in algebra. All right. Problem 2 is we have permutations written as a product of cycles and write them as a product of disjoint cycles. So here in the first one, I have sigma is 1, 2 times 2, 3. So these are 2 cycles or transpositions, but they're not disjoint because there's a 2 in each. If you want to write this as a product of cycles, let's just start with a cycle. What happens to 1? This sends 1 to 1. This sends 1 to 2. So 1 ends up to 2. This sends 2 to 3, and this sends 3 to 3. So 2 goes to 3. This sends 3 to 2. This sends 2 back to 1. So this permutation is just a 3 cycle. So it's a product of 1 cycle, which is perfectly legit. Let's look at B. In B, my permutation sigma is 1, 2, 3 times 3, 2, 1. So it's this function followed by or composed with this function. So this sends 1 to 3. This sends 3 back to 1. So 1 just goes to 1. This sends 2 to 1. And then 1 goes to 2. So 2 goes to 2. This sends 3 to 2. And this sends 2 to 3. So this permutation is the identity. 1 to 1, 2 to 2, 3 to 3. So if I look at this permutation, it's the identity. And that also says that the inverse of 1, 2, 3 is 3, 2, 1. Because this times this is the identity. Each of these is the inverse of the other. Any questions so far? In C, we have 1, 2, 2, 3, 4, 4, 5. So let's see what happens in this permutation. We want to write it as a product of a cycle or cycles. Start with 1. This sends 1 to 1. This sends 1 to 1. And this sends 1 to 2. So 1 ends up with 2. This sends 2 to 2. This sends 2 to 3. This sends 3 to 3. 3 goes to 3, goes to 4, stays at 4. 5 goes to 4. 4 goes to 2. 2 goes to 1. Oops, sorry. 4 goes to 5, to 5 to 5. Okay. And 5 goes to 4, 4 goes to 3. No, sorry. 5 goes to 4, 4 goes to 2, 2 goes to 1. So this product of 3 non-disjoint cycles is just the 5 cycle, 1, 2, 3, 4, 5. Suppose I take 1, 2, 3 times 2, 3, 4. Again, you always have to remember a permutation is a function, and this is composition of functions. So this sends 1 to 1, and then 1 to 2. So 1 ends up at 2. This sends 2 to 3, and 3 goes back to 1. So I just have a 2 cycle. This sends 3 to 4, 4 to 4, so 3 goes to 4. This sends 4 to 2, and this sends 2 to 3, so 4 ends up at 3. So this product of 3 cycles is equal to this product of 2 transpositions. Okay. You're just following numbers around. And finally, we have a product of a 5 cycle times this 4 cycle. This sends 1 to 1 to 2. 2 goes to 2 goes to 3. 3 goes to 3 goes to 4. 4 goes to 5. And 5 goes back to 1. So we have a cycle 1, 2, 3, 4, 1, 2, 3, 4. We haven't looked at 5 yet. 5 goes to 6, goes to 6. 6 goes to 7, goes to 7. 7 goes to 4, and 4 goes to 5. So this is a product of these 2 disjoint cycles, 1, 2, 3, 4, 5, 6, 7. Any questions about this?
Professor, I guess just on the 7 one, so you would, I guess my only thought was initially I thought 7 would go to 4.
Right, so this
you
is
wouldn't put
composition
4
of
in both.
functions.
Yeah.
So 7 goes to 4, and then 4 is sent to 5, so 7 ends up at 5. So 7 comes around.
Okay, understood. I missed that one. Okay, thank you.
Okay. Problem 3, we have, let me take a piece of paper. In problem 3, we have the permutation alpha. These are permutations in S4, 2, 3, 4, 1. And sigma is 3, 4, 1, 2. And we want to compute the permutation tau, which is alpha sigma alpha inverse. Of course, we have to know this is alpha, this is sigma. We have to know what is alpha inverse. So alpha sends 4 to 1, so the inverse sends 1 back to 4. Alpha sends 1 to 2, so the inverse sends 2 to 1. Alpha sends 2 to 3, so the inverse sends 3 back to 2. And alpha sends 3 to 4, so the inverse sends 4 back to 3. So that's alpha inverse. So this
To 3, right? So just it looks like 4 to 4. But it's 4 to 3.
Yes, thank you. So this is alpha times sigma times alpha inverse. And we just follow things around, always going from right to left. 1 goes to 4, 4 goes to 2, 2 goes to 3. 2 goes to 1, 1 goes to 3, 3 goes to 4. 3 goes to 2, 2 goes to 4, 4 goes to 1. 4 goes to 3, 3 goes to 1, 1 goes to 2. So alpha sigma alpha inverse is this, which somewhat remarkably is exactly the same as sigma. And suppose I want to write sigma and tau as products of disjoint cycles. Well, if I did my calculation correctly, sigma equals tau. So as a product of disjoint cycles, sigma or tau is what? 1 goes to 3, 3 goes to 1. 2 goes to 4, 4 goes back to 2. So both sigma and tau are the products of these two transpositions. Let's see. I could do more of these calculations, but let me look at some other types of problems here. Let's look at number 6. So in a group, sigma in G, we say it has order K if K is the smallest positive integer such that sigma to the K is the identity. So if you let sigma be a cycle of length K, so suppose sigma is A1, A2, A3 up to A sub K in SK. So the A1 up to A sub K, so in SN, are distinct integers between 1 and n. And what happens if you compute sigma to the K? This means sigma times sigma times sigma times sigma times sigma, K times. You iterate this K times. So what happens when you apply sigma to K, for example, to A1? A1 goes to A2, again to A3, do it again to A4, K minus 1 times, you have AK, and K times comes back to A1. This is the identity. If you think of this as, if you draw your cycle as a picture, if you understand it that way, which is a good way, if you have sigma is A1, A2 up to A sub K, it's like you have the numbers A1 goes to A2, goes to A3, goes to A4, goes to A sub K minus 1, goes to A sub K, goes back to A1. This is sort of a picture of how your cycle works. Goes around the circle. And there are K steps that bring you back to where you started. You start with A2 and you go K times around, you're back at A2. So sigma to the K sends every element to itself. So a cycle of length k has order k. Let's look at some of the problems on matrices. For example, number 9. So we have 3 matrices. A is 2 minus 1, 3, 2. B is 0, 3, minus 9, 2. And C is minus 5, 1, 1, 3. So these are just 2 by 2 matrices with integer coefficients. They don't have determinant 1, so they're not in that group SL2, but they're just 2 by 2 matrices, and you can multiply them and see if you can take their inverses. So what is the product AB? 2 minus 1, 3, 2, 0, 3, minus 9, 2. So this is 0 plus 9 is 9. 6 minus 2 is 4. 0 minus 18. 9 plus 4. So if I multiply correctly, that's AB. BA is what you get when you multiply in the opposite order. 0, 3 minus 9, 2. 2 minus 1, 3, 2. So this is 0 plus 3 is 9. 0 plus 6 is 6. Minus 18 plus 6 is minus 12. 9 plus 4 is 13. So if I did this arithmetic correctly, this is what I get. And you'll notice AB is different from BA, because in general, matrix multiplication is not cumulative. What is A inverse and what is B inverse? So if A is the matrix A, B, C, D, and the determinant AB minus BC is not 0, then the inverse is, let me call this determinant delta, say. If the determinant were 1, you would get the inverse by interchanging A and D and changing the signs of B and C. And you divide each coordinate by delta, by the determinant. We just looked at this for delta equal to 1, but this is what it is in general. So if you take A, the determinant of this matrix A is 2 times 2 minus 1 times 3. That's 4 plus 3, or 7. So A inverse is what? You interchange the diagonal elements. They're the same, so they don't really change. And you change the signs of the opposite diagonal elements, and you divide by this determinant 7. And this should be the inverse. Let's just check. Suppose I take A inverse. So A is 2 minus 1, 3, 2. A inverse is 2 sevenths, 1 seventh, minus 3 sevenths, 2 sevenths. So this is 2 sevenths times 2. 4 sevenths plus 3 sevenths is 1. This is 2 sevenths minus 2 sevenths is 0. This is 6 sevenths minus 6 sevenths is 0. 3 sevenths plus 4 sevenths is 1. So I get the identity matrix. So that says that this calculation is correct. This is A inverse. It's A times A inverse is the identity. Questions about this? Yeah. What about number? I mean, there are more multiplications of matrices, but this is all really calculations that you just have to learn how to do. Problem number 10 is to prove an important fact about the determinant of a matrix. If I have X is the matrix A, B, C, D, what we call the determinant of X, or the determinant of the matrix A, B, C, D, is AD minus BC. So if we have X is A, B, C, D, and another matrix Y, which is E, F, G, H, we want to prove that the determinant of the product is the product of the determinants. So this is a calculation that's important to do periodically, just to make sure you absorb the fact that this determinant of matrices is multiplicative in a sense. What is the product of X and Y? That's A, B, C, D times E, F, G, H. When you multiply these matrices row into column, you get A, E plus BG, AF plus BH, CE plus DG, and CF plus DH. That's the product. So the determinant of X times Y, it's this times this, AE plus BG times CF plus DH, minus this times this, AF plus BH times CE plus DG. So that looks like a sort of a mess to calculate, but we still have to calculate it. So this just distribute across and see what we get here. This is just multiplying in the form A plus B times C plus D. This is AECF or ACEF plus ADEH plus BCFG plus BDGH. That's this when you multiply it out. Minus, and then let's multiply this out, you get ACEF plus ADFG plus BCEH plus BDGH. And then we notice that there's a little bit of cancellation because here I have ACEF and here I have ACEF, so they cancel. And here I have BDGH and minus BDGH, so they cancel. So I seem to be left with just these four terms. So that's ADEH plus BCFG minus ADFG minus BCEH. So let me just play with this a little bit. Here I have ADEH and here I have minus ADFG. So that's ADEH minus FG. And here I have BCFG and minus BCEH. So I can write that as minus BCEH minus FG. Okay, so this is just high school algebra done hard. And here I have EH minus FG and EH minus FG. If I factor that out, I get AD minus BC times EH minus FG. And then a miracle happens. If X is A, B, C, D, the determinant of X is AD minus BC. This is the determinant of X. And the determinant of Y is EH minus FG. So I've just proved what I wanted to prove. The determinant of XY is determinant of X times determinant of Y. Any questions about this? Problem number 11 is to look at the group which I call SL2R. So this is all matrices A, B, C, D, where A, B, C, and D are real numbers, not just integers, and the determinant AD minus BC is 1. So if I take, let's say X equals A, B, C, D, and Y equals E, F, G, H, then, and I multiply them, the determinant of X times Y by what I just calculated is the determinant of X times the determinant of Y. And each of these is 1, and 1 times 1 is 1. So if X and Y are in SL2R, then the product X times Y is in SL2R. So this set of matrices is closed under multiplication. The inverse of X, X has determinant of 1, is D minus B minus C A. And the determinant of X inverse is D times A minus B times minus C. DA is AD, minus times minus is plus, minus, this is also 1. So if X is in SL2R, then X inverse is in SL2R. The identity is the identity matrix 1, 0, 0, 1. So this set of matrices is closed under multiplication and taking inverses. It contains the identity. And so it's a group. So we've proved, and we know that matrix multiplication is associative. That's just another calculation, but we proved it, certainly proved in the notes. Questions about this? Problem 12, we look at G as a certain set of matrices, A, 2B, 3C, and D, where A, B, C, and D are now integers, and the determinant AD minus 6BC is equal to 1. So these are matrices with integer entries and determinant 1. So G is contained in this group SL2Z of 2 by 2 matrices with integer coordinates and determinant 1. And I want to show it's a subgroup. It's a group with matrix multiplication. So I have to show there's closed under. So this means this is, you're looking at matrices with integer entries. where this coordinate is divisible by 2 and this coordinate is divisible by 3. Suppose I take two matrices of these forms, say A, 2B, 3C, and D, and let's say E, 2F, 3G, and H. When I multiply them together, what do I get? I get AE plus 6BG, A times 2F plus 2 times BH, 3CE plus 3DG, and 6CF plus DH. I get this matrix. But you notice this is equal to this number, that's an integer, AE plus 6HG. This is 2 times AF plus BH. This is 3 times CE plus DG, and this is 6CF plus DH. So this is a matrix where this coordinate is a multiple of 2, this coordinate is a multiple of 3. We know the determinant is 1 because this is a product of two matrices of determinant 1. If I take A, 2B, 3CD inverse, that's, I interchange the 2 and the A, I change the sign, 2B is 2 times minus B, 3C goes 3 times minus C. So this is again a matrix where this coordinate is even and this coordinate is a multiple of 3. So this set of matrices is closed under products and taking inverses, and it contains the identity, so it's a subgroup. It's a group of SLTs. Any questions about this? Okay. Problem number, let's see. Let me do some of the problems on number theory. Yeah, actually, let me do a problem on set theory. So this is problems in set theory and number theory. So I have sets R, S, and T. Suppose I want to prove that S prove that R union S intersect T is R union S intersect R union T. Let's just draw a picture to try and see what's going on before we start the proof. So suppose this is R, this is S, and this is T. So S intersect T, this is S, this is T. So this in the orange is S intersect T. So if I take R union S intersect T, that means everything that's either in R or S intersect T, it's all this. R union S with everything in there. So the green is R union S. R union T is everything in blue. So if I look at the intersection of everything in green and everything in blue, what do I get? So I have everything, see, R union T, that was a blue color, R union S. So R union S was this. Well, that was R union S, and R union T so the intersection of the blue and the green, just this. Yeah, looks like R union S intersect two. No, that's just a picture. It's hard to maybe understand the picture, but I think it gives some insight. But let's prove this. So suppose X is an R union S intersect T. So that means that either X is in R or X is in S intersect T, which means that either X is in R or one of these two things happens. X is in S and X is in T. So either if X is in R, then it's certainly in R union S, and it's certainly in R union T, because it's in R, so it's in both of these sets. Or X is not in R, in which case it's in both S and T. X is in S intersect T. Okay, this is all correct, but I'm going to say it in a little bit better way. So let me start this again. I want to show that these two sets are equal. So I want to show that each set is a subset of the other. So if X is an R union S intersect T, then there are two possibilities. Either X is in R or X is in S intersect T. If X is in R, then X is certainly in R union S and R union T, because each of these contains R. So X is in the intersection of these two sets. And if X is in S and T, then X is certainly also in R union S, because it's in S, and in R union T, because X is in T, so it's in the intersection. So in both cases, X is in this right-hand side. So that proves that the left-hand side is contained in the right-hand side. And now we have to prove that if something is in the right-hand side, it's in the left-hand side. So if X is in R union S intersect R union T, then this means that X is in R union S and X is in R union T, which means either X is in R, but if it's not, then X is in S and x is in t, which means x is in R or x is in S intersect t, which means x is in R union S intersect t. And that's the proof. Questions about this? Let's see, what about problem 2? No, problem 3. Suppose I take the numbers A equal to 196 and B equal 518. So I want to find their greatest common divisor. And the Euclidean algorithm just means divide one into the other and iterate that until you get the remainder. So if I divide 518 by 196, I think that's 2 times 196, which is just a bit under 400, plus a remainder of 126, I think. Right? So this is, I'm writing 518 as some quotient, Q times 196Q, plus the remainder, which is 126. And then I take 196 and I divide it by 126. That goes one time and leaves a remainder of 70. And I take 126, I divide it by 70, and that goes in one time and leaves a remainder of 56. And if I divide 70 by 56, that goes in one time and leaves a remainder of 14. If I divide 56 by 14, that goes in exactly 4 times and leaves a remainder of 0. So the last positive remainder is the GCD, the greatest common divisor of 196 and 518 is 14. And if I want to write 14 as a linear combination of these two numbers, I just work backwards from this. 14 is 70 minus 56. And 56 is 120 minus 70. So this is 2 times 70 minus 120. And from this, 70 is 196 minus 126, which is 2 times 196 minus 3 times 126. And from this, 126 is 518 minus 2 times 196. And 3 times 2 is 6 plus 1 is plus 2 is 8. So this is 8 times 196 minus 3 times 518. So here I've written 14 as a linear combination of 196 and 518. And that's the solution to problem 3. Okay, any questions about this? So congruences are very important in algebra. So let's look at number 8. We want to find a set of odd numbers that is a complete system of residues modulo 9. So let's just recall the definition. You have a positive integer m, a complete system of residues modulo m is a set of m integers, positive, negative, or 0, R1, R2, up to R sub m, or maybe, yeah, such that every integer a satisfies a is congruent to R sub I mod m, or the set capital R, for some number Ri in the set. So the standard example is you take R to be the integers from 0 to m minus 1. So if m equals 9, one complete system of residues would be 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is a complete system of residues modulo 9. Because if you take any integer and divide it by 9, the remainder is one of these, and every number is congruent to its remainder. But these numbers are not all odd. I have even numbers in here. And the problem is to find a set of odd residues. So what can we do? Well, I want to replace 0, 2, 4, 6, and 8. So 9 is congruent to 0 mod 9. So anything congruent to 0 is also congruent to 9. 2 is congruent to 11 mod 9, for example. 4 is congruent to, I could say 13 mod 9. I could also say 4 is congruent to minus 5 mod 9. There are lots of choices. 6 is congruent to 15 mod 9. I could also say 6 is congruent to 33 mod 9. These are all odd numbers. So I could take R to be equal to 9, 1, 11, 3, 13, 5, 15, 7. Let's see. 8 is congruent to 17 mod 9, 17. This would be one set of odd numbers that's a complete system of residues. Or I could, but there are infinitely many choices. I could take R to be 9, 1, 11, 3, minus 5, 5, 33, 7, 17. I mean, there are many choices. These are all examples of sets of 9 odd numbers, each of which is a complete system of residues modulo 9. Let's look at number 9. We want to find the smallest positive integer k such that if a is an integer relatively prime to 8, then a to the k is congruent to 1 mod 8. So what does it mean to say a number is relatively prime to 8? A and k are relatively prime if and only if a is odd. Right? Because an even number has common divisor at least 2 with 8. And every odd number is congruent to 1, 3, 5, or 7 mod 8. 1 to the first power is 1 mod 8, of course. 3 squared is 9, is congruent to 1 mod 8. 5 squared is 25, is also congruent to 1 mod 8. And 7 squared is 49, is also congruent to 1 mod 8. So that means a squared is congruent to 1 mod 8 for all a such that a and 8 are relatively prime. So the answer to problem 9, part A, is 2. A squared is 1 mod 8 for every odd number a. Any questions about this? What about part B? We want to solve the same type of problem for the modulus 12. So we want to find the smallest integer k positive such that a to the k is congruent to 1 mod 12 if 12 and a are relatively prime. Now, the Euler phi function, phi of 12, if you calculate it, is 4. A and 12 are relatively prime if and only if a is congruent to either 1, 5, 7, or 11 mod 12. So we just have to find the smallest power of each of these numbers, which is congruent to 1 mod 12. So 1 to the first power, of course, is always 1 mod 12. What about 5? 5 squared is 25, is congruent to 1 mod 12. Because 25 minus 1 is 24, is divisible by 12. 7 squared is 49. Take away 1, you get 48 is 4 times 12. So this is congruent to 1 mod 12. And 11, well, you can say 11 squared is 121, which is 12 times 10 plus 1 is congruent to 1 mod 12. So the answer is k equals 2. So we did this problem for moduli 8 and 12, and part C is the modulus 11. We want to find the smallest k, at least 1, such that whenever a and 11 are relatively prime, then a to the k is congruent to 1 mod 11. Now, phi of 11, the number of integers up to 11 relatively prime to 11 is 10. So a, take any of the numbers from 1 up to 10, these are all, every number in here is relatively prime to 11. Of course, 1 to the first power is certainly 1 mod 11. But we want to, for example, find k such that 2 to the k is congruent to 1 mod 11. That's not so obvious. What are the powers of 2? 2, 4, 8, 16, 32, 64. What are these congruent to mod 11? This is congruent to 1, congruent to 4, congruent to 8. 16 is congruent to 5. 32 is congruent to mod 11, 10, which is the same as -1. 64 is 2 times this is congruent to -4, -2. 128, 256, 512. But 128 is 2 times 64, that's congruent to -4. This is congruent to -8. 512 is congruent to -16. 1024, this is already 2 to the 10th, it's congruent to -32, which is congruent to 1 mod 11. So the smallest k that satisfies this is k equal 10. So already we're looking at big numbers. What about 3 to the k congruent to 1 mod 11? We can look at the powers of 3, 9, 27, 81, 243. Let's see, 3 is congruent to 3 mod 11. 9 is congruent to 9 mod 11. 27 minus 5 is 22, which is divisible by 11. So 27 is congruent to 5 mod 11. 81 that's 3 times 27, that's congruent to 15. I just multiply this by 3, which is congruent to 4. 243 is congruent to 12, which is congruent to 1 mod 11. This is 3 squared, this is 3 cubed, this is 3 to the 4th, this is 3 to the 5th. So the smallest k, such that 3 to the k is congruent to 1 mod 11, is k equal to 5. And you have to do this calculation for all of the numbers from 1 to 10. I just did 1, 2, and 3. It's a tiny bit of work. And when you do this, you'll find that the smallest power of k, such that a to k is congruent to 1 mod 11, is always either 1, 2, 5, or 10. And 10 occurs, for example, when you choose 2 to the power k. So the answer to the problem is k equal 10. 10 is the smallest power, such that a to the 10th is congruent to 1 mod 11 for every number relatively prime to 11.
Sorry, can you say that one more time? So if 3 goes to the power of 5, I would have thought that was the smallest, but it has to encompass.
No. So for the number 3, 3 to the 5th is congruent to 1 mod 11. And then automatically 3 to the 10th, that's 3 to the 5 times 2. Right? Because 10 is 5 times 2. That's 3 to the 5th squared. 3 to the 5th is congruent to 1, so that's 1 squared, which is congruent to 1 mod 11. So for the number 3, the smallest power of 3, which is congruent to 1 mod 11, is the 5th power, but the 10th power also works. So 3 to the 10 is congruent to 1 mod 11. For the number 2, the smallest power is 10. 2 to the 10 is congruent to 1 mod 11. And in general, you just have to do the calculation. For all a, which are relatively prime to 11, a to the 10th is congruent to 1 mod 11, and 10 is the smallest number that has this property. Because it can't be smaller than 10 because 2 requires
Right,
exponents.
won't work. Perfect, thank you.
Let's look at problem 10. So we want to compute the addition and multiplication tables for the integers mod 6. So representatives, each congruence class mod 6 is 0, 1, 2, 3, 4, or 5. And I want to know what happens when you add these appropriate congruence classes. So if you add 0 to anything, you just get back what you're adding. If I add 1 to 0, I get 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. 1 plus 5 is 6, which is 0 mod 6. 2 plus 0 is 2. 3, 4, 5. 2 plus 4 is 6, which is 0. 2 plus 5 is 7, which is 1. And so forth. 3 plus 3 is 0. 3 plus 4 is 1. 3 plus 5 is 2 mod 6. So if you work out the addition table, this is the addition table. Modulo 6. And what about the multiplication table? For 0 times anything is 0. That's easy. And 1 times anything is just the anything. And anything times 1 is the same thing. So the interesting part of the table to fill in is this little bit. So 2 times 2 is 4. 2 times 3 is 6, which is 0. 2 times 4 is 8, which is 2 mod 6. 2 times 5 is 10, which is 4. 3 times 2 is 6, which is 0. 3 times 3 is 9, which is 3. 3 times 4 is 12, which is 0. 3 times 5 is 15, which is 3 mod 6. 4 times 2 is 8, which is 2 mod 6. 4 times 3 is 12, which is 0. 4 times 4 is 16, which is 4 mod 6. And 4 5s are 20, which is 2 mod 6. 5 2s are 10. 10 is 4 mod 6. 5 3s are 15. That's 3 mod 6. 5 4s are 20. That's 2 mod 6. 5 times 25 is 1 mod 6. So this is the multiplication table. When you're looking at congruence classes mod M, you can add and you can multiply congruence classes. So you have an addition table and a multiplication table, and m equals 6. Here they are. Problem 13 is to solve some congruences. First is 9x congruent to 15 mod 21. So how do we solve this? Well, 9x is congruent to 15 mod 21 if and only if 9x minus 15 is some multiple of 21, is 21 times y for some y. Of course, I can divide this. We're looking for integer solutions. I can divide this by 3. That's the same as saying x and y satisfy 3x minus 5 equals 7y. Well, if and only if 3x is congruent to 5 mod 7, that is, I could just have divided all these numbers by 3. What's the solution of this congruence? Well, you can just do it by trial and error because you only have 7 numbers to choose from. 0 doesn't work. 1 doesn't work. 2 doesn't work. 3 doesn't work. 4. 3 times 4 is 12. 12 minus 5 is 7. So if and only if x is congruent to 4, mod 7. And you can check 9 times 4 is 36. It's 15 plus 21. So 9 times 4 is congruent to 15, mod 21. That checks. What about B? How do we solve 8x congruent to 15 mod 26? So 8, 15, and 26 don't have a common divisor. You could just try all numbers from 0 to 25. That's a lot of work. But you should recall the theorem that says ax congruent to b mod m as a solution if and only if b is congruent to 0 modulo the greatest common divisor of a and m. So in this case, a is equal to 8, b is equal to 15, m is equal to 26. The greatest common divisor of a and m is the greatest common divisor of 8 and 26, which is 2. And b equal 15 is not congruent to 0 mod 2. So this congruence has no solution. So you don't have to waste your time by trial and error. There's no solution. Any questions? Let's look at part C. Solve the congruence 14x congruent to 21 mod 17. So the greatest common divisor of 14 and 17 is equal to 1. So this congruence has a solution. In fact, it has a unique solution, mod 17. How do we find it? It's kind of complicated. So one way to do it, I mean, it's always trial and error, but another way to do it is the following. If 14 and 17 have greatest common divisor 1, that means you can write 1 as some linear combination. I'll write it 14 u plus 17v. Yes. Our basic theorem about the greatest common divisor of two numbers is that it's always an integral linear combination of the numbers. So if I multiply this by 21. 21 is 14 times u times 21 plus 17 times v times 21. So this is congruent to 14 times 21u mod 17. So I take my x to be 21u. So if I can write 1 as a linear combination of 14 and 17, I'm done. Then I'm halfway done. So how can I write 14 and 17, a linear combination of 14 and 17 equal to 1? Well, sometimes you're lucky and you can find an answer. Otherwise, you have to do some work. You can always use the Euclidean algorithm that we used a moment ago. 17 is 14 times 1 plus 3. 14 is 3 times 4 plus 2. 3 is 2 times 1 plus 1. So if I take this and work it backwards, 1 is 3 minus 2. That's 3 minus, and 2 is 14 minus 3 times 4, which is, this is 4 times 3 plus 3 is 5 times 3 minus 14. And this says 3 is 17 minus 14 minus 14. So this is 5 times 17 minus 6 times 14. In other words, 1 is equal to 14 times 6 that's minus 14 times 6 plus 5 times 17. If I multiply this by 21, actually I can take a shortcut. I can notice that 21 is congruent to 4 mod 17. So I can also solve 14x congruent to 4 mod 17. Let me multiply this by 4. 4 is equal to 14 times minus 6 is minus 24 plus 17 times 5. So that says that 14 times minus 24 is congruent to 4, which is congruent to 21 mod 17. So one solution is x is minus 24. Of course, minus 24 is congruent to minus 7 mod 17, which is congruent to 10 mod 17. So another solution, let me just write it over here, would be 14 times 10 is congruent to 21 mod 17. Let's just check. 14 times 10 is 140. 140 minus 21 is 119. 119 is 17 times 7. So it works. So the simplest answer to this problem is all x congruent to 10 mod 17. Okay. Let's look at number 14. I want to find all numbers such that x is congruent to 2 mod 5, and at the same time, x is congruent to 3 mod 7. So to say x is congruent to 2 mod 5 means x is 2 plus 5y for some y. X congruent to 2 mod 5 means x is 2 plus 5 times y. And so if x is congruent to 3, that means 2 plus 5y is going to be congruent to 3 mod 7. So that means 5y is congruent to 1 mod 7. The solution of this is easy. Any number which is congruent to 3 mod 7, because 15 minus 1 is 14 is divisible by 7. So y is any number that form 3 plus 7 times z. So plug that in here, you get x, which is 2 plus 5y, is 2 plus 5 times 3 plus 7z. This is 2 plus 15 is 17 plus 35z. So any number, so the solution is all x congruent to 17 mod 35. Let's check. 17 is congruent to 2 mod 5, because this is 15 is divisible by 5. And 17 is congruent to 3 mod 7, because 14 is divisible by 7. So it checks. So that's the solution. Let's look at 14b. We want to solve the system x congruent to 2 mod 15 and x congruent to 3 mod 21. So if x is congruent to 2 mod 15, that means x is a number of the form 2 plus 15y. And if 2 plus 15y is x, is congruent to 3 mod 21, this means 15y is congruent to 1 mod 21. And that would mean that 15y is 1 plus some multiple of 21. But this is impossible, because this is divisible by 3 and this is divisible by 3, but 1 is not divisible by 3. So this system of two linear congruences has no solution. Any questions about this? Any other problems you'd like me to go over? So I do have an office hour today. I have 2 office hours tomorrow. One of them is in the evening for people who have classes all day long. So if there are things you would like me to go over in addition to what I've just done, you should log into an office hour. If you're not available at any of those 3 times today and tomorrow, send me an email and we can arrange some additional times when I'm online. But the median number of people who show up for a problem session online is 0 or 1. So not many people are taking advantage of the time when you can just ask me to go over as much as possible. Whatever you want. All right, so the midterm is on Wednesday from 9 to 11. I will post it on Blackboard and email it to everyone a few minutes before 9. And you have 2 hours to answer questions and turn them in. Anything else I should go over? I'm happy to do more problems if there are any questions. Okay. If not, then we are done for the morning. It is the first full day of spring, so enjoy the day. Bye, everyone.
Thank you, Professor.
Bye, thank you.
Professor, I have a quick question.
Sure.
Well, it's not related to exam, because remember I emailed you about my extended time.
Yes,
So you said the exam is 2 hours, right?
correct.
So for me, my extended time is a time and a half. So would that mean I have 3 hours?
Yes.
3 hours. Okay, thank you.
Yeah, no problem at all.
Have a nice day, Professor.
Thank you. You too. Bye-bye.
Bye.